All right, here we're going to look at the inclined plane, and we're going to look at all the forces at play on this inclined plane as I'm pushing this mass up the inclined plane, and it's going to have an acceleration of a constant acceleration. What are the forces at play? So the first thing is you're going to see, first thing we have to note is that gravity is at play, so that is pulling that, wants to pull it down, right, with mg, with a force of mg. However, that mg can be broken into two pieces. First of all, you have the piece which is perpendicular to the plane, and remember this angle there is theta, so therefore we have mg cos theta. That's the force perpendicular to the plane, because the plane is actually has an angle of theta. And there's a force horizontal to the plane, which wants to pull the object back down, and that's going to have a force of mg sine of theta, just from trig, right? There's a right triangle here. In addition, when you're pushing, so assuming you're pushing horizontally with the level ground, if you're pushing horizontally with level ground, your force has two components. When you're pushing, it has a component that's horizontal to the plane and a component that's also vertical to the plane. And so the horizontal piece to the plane, again, this is theta, again, that angle there. So the component horizontal is going to be mg cosine of theta, sorry, f cosine of theta, f cosine of theta. And the component that's vertical to the plane, perpendicular, is going to be f sine of theta. So you have these two forces as well, that your push, your force, that's what the two pieces are. So now, how do we put this all together? So this object is moving up in an acceleration. So the net force on it is mass times acceleration. So mass times acceleration is the end result of all these different forces. And what is it? Well, first of all, let's think about the horizontal forces. The horizontal forces is f cosine of theta, and that's actually the only force that's moving it up. So that's going to be f cosine of theta, moving it up the plane. But it has a resistance. That f cosine of theta, first of all, horizontally is resisted by mg sine of theta. So we have to subtract that, mg sine of theta. That's the force down here. Okay. Now, if there were if this was frictionless, that would be it. But we have friction going on, and there's a coefficient of friction called mu. So mu is the coefficient of friction. And so that mu, that has an effect, that resists our push. So that mu has applied to two things. First of all, we have the normal force from the object itself, which is going to be mg cos theta, that's the normal force. So mu times mg cos theta, mu times this one here, is going to give me the resistance from the object. So we have to subtract that off, minus mu mg cos theta. And we also have resistance from our own push, because we're pushing somewhat down on the object. So there's a force that's resisting from that f sine of theta. There's a friction from that, because we're actually creating more force perpendicular to the plane on that object by pushing at this angle. So we have to subtract that off, which is mu f sine of theta. So that's that last piece. So that's the setup for the inclined plane. If that object is going to move at a constant acceleration, that's the setup of all the forces that are at play in this problem. And then you have to know, well, which ones are which. You might be given different values, and then you figure out the rest from there. But that's the basic setup for the inclined plane.